Hello, have a nice day. Today I am going to show you how to do some comparative analysis in a transformer by using PSPICE. So what is a transformer? In transformer we have two inductors. Those are coupled to each other. Those are mutually coupled by using an iron core or air or whatever the method. Transformers are using to step up or step down alternative currents. It is not necessary to be an alternative current. Even transient waveforms we can transfer from primary to secondary. We can transfer energy from primary to secondary. Electrical energy, then magnetic energy, then again it converts to electrical energy. So today I am going to take an example of a transformer and its equivalent circuit. It's referred to primary circuit in many ways by using PSPICE. Okay, let's start the simulation. So first of all, I would like to select an ordinary transformer. Place PSPICE components, search here, this is already there, and I can search for an inductor because transformer is two inductors. Right? Inductor transformer is basically a mutual coupling in between two inductors, right? So inductor coupling transformer here. So this is my ideal transformer. In this transformer model we don't have any resistance, we have only inductance values. So we can double click this transformer and we can set the primary winding inductance and the secondary winding inductance. So I would like to set my primary winding inductance as 1 millihenry and my secondary winding inductance as 10 millihenry. No, 100 millihenry. I just gave some arbitrary values. So why 1 millihenry and 100 millihenry? Because I just gave those values, and you know this relationship in between inductance and the turns ratio, N secondary over N primary squared is equals to L secondary over L primary with a given reluctance path. So if I can maintain my secondary to primary inductance ratio at 1 to 100 to 1, then my turns ratio becomes 10 to 1, right? So that is why I just choose 100 as my secondary inductance and 1 millihenry as my primary inductance. So right, so then I would like to select my source, PSPICE components, sources, voltage source, sine wave, right? Just give some arbitrary values. Amplitude I would like to give 230 volts. Frequency let's give 50 hertz. This is 0. If you want to know what are these values, just Google. Then I need some resistors. Place PSPICE components resistor. This is my primary winding resistor, leakage resistance, not leakage resistance, primary winding resistance, and also I need some ESR component to my voltage source. I would like to set this to a very small value. Let's say 50 milli, and this is primary winding resistance. I just set it as 0.1 ohms, and my secondary winding resistance, I need to set some winding resistance values because this transformer is an ideal one. So my secondary winding resistance, I set it as 10 ohms. Why I select those values like that? Primary winding resistance is lower than secondary winding resistance because I would like to build a step-up transformer. For a step-up transformer, I need more windings to my secondary. Because of that, I might get much higher resistance in my secondary winding. So, right, in tally with some practical values, I put those things. Right, and my load resistance, just press control and drag and drop. When I press R button, it will rotate. So my load, I would like to set it to 1 kilo ohms, and pressing W will give me the chance of connecting these devices, these elements. And this is the ground. And my secondary. Right. W. And also here this secondary circuit is electrically isolated, so in order to simulate this profile we need some kind of reference to this secondary winding. For that I would like to introduce some big resistance in between our ground value and the secondary side wire, otherwise the simulation will give you some errors. So this resistance, I set it as 1 giga ohms. Right. Now I would like to measure the voltage across my load. Voltage across my load means voltage in this point with respect to the ground, right? Or else I can use this differential probe anyway. And the input to the transformer. Right. This is now 1 to 10 turns ratio step up transformer. Now I can simulate this profile. I set the simulation time 0.1 seconds, and here in the options I set this to 10 to the power minus 5. If I reduce more and more, my curves, my plots will be more smooth. Right. Right. I can change the resolution by using that. Anyway, now when I run the simulation, I should see something similar to output from a step-up transformer. Right, so red color is my input waveform and green color I can see my output waveform. Yes, this is step-up transformer. How much? Input is nearly 100 volts, isn't it? no 230 volts, yes, nearly, and output is 2000 volts. Yeah, 10 times step up. Why those values are not matched 100%? Because of these added resistance values. In order to make some practical transformer, I add these values, right? So because of that, we don't have perfectly matching 1 to 10 step up transformer, right? When I measure the voltage values here and here, it should give me exactly 1 to 10, because this is the ideal part of the transformer, right? Now let's see. Yes, now when first part we can omit because of those inrush currents and those things, it is somewhat differ from the practical, from the other values. So here this is almost 100 volts, sorry, 200 volts, 210 roughly, here 2100 nearly, so 10 times step of transformer, right? Now this is the first method that I can build a transformer. Now I would like to build this in another way. Now let's see whether there is any other module, right? There are more modules, inbuilt modules in PSPICE. Let's move it here. And also, if you want more space in this schematic diagram, you can go to options, schematic page properties, and you can select your required amount of space, right? So I selected B, right? Now I would like to draw the same transformer circuit by using inductors, by using general inductor, right? Here this is the inductor here. There are plenty of elements here. Place PSPICE component, you have inductor here, right? I placed it here. You can see when we place an inductor, there we can see this dot notation, right? This is my primary winding and my secondary winding is this. My primary winding inductance is 1 millihenry and secondary winding inductance is 100 millihenry. Right. So these two are independent mutually independent. So in order to get coupling in between these two, I need to add some mutual coupling. Here we have different types of couplings. How about searching magnetics? Magnetic cores. Yeah. Firstly, try coupling, linear coupling. So my first inductor is L1 and second one is L2. This is my coupling in between L1 and L2. In order to couple these two inductors, I need to go to the property editor and I have to select what are the two inductors that I'm going to couple, L1 and L2. I can mutually coupled up to 6 inductors by using this coupling, right? Inductance 1 is L1, inductance 2 is L2. If this is L3 and this is L4, I can set L1 as L3 and L2 as L4, right? So this is my primary and secondary inductance, right? So then I have the same winding resistance. I can copy the whole thing and change that winding. I delete this and replace my mutually coupled inductor. Right. Now I should get the same input and output. I should get the same output. Here also we have to introduce this resistor. Right, now let's see the output and input. Why an error? L1, L2, right, save. Let's change the resolution, simulation, resolution, check. Why an error? Oh. It's because of this. No. Why? What cause an error? Give me some time. Oh, very sorry. The error is right. Really sorry. Error is because of this resistor. Right. Now let's simulate this. And see. Right. So I get the same variations of input and output of the transformer. Right. Let's see the output of this transformer and the output of my next transformer, whether those two are identical or not. Right, you can see those two are perfectly identical, perfectly matched. Right, that means these two circuits are identical. Right, that means this mutual coupling thing is working. Right, so let's see another approach, how to build this same transformer in another way. Right, so how to do it? Let's search for a transformer. Right, here we have lots of transformers. No. If I want to model my own transformer, what I can do is place PSPICE component, modeling application, system modules. I can build my own transformer with my own parameters right here. So by using this interface, I can generate my own transformer. I can give some model name, primary winding inductance. The same inductance I am interested to give, what is the value? 1 millihenry. Here it says primary winding inductance in Henry, right? 0.001. 1 millihenry. Primary winding resistance 0.1 ohms. Secondary winding resistance in ohms 10 ohms. Turns ratio I would prefer 10. Leakage inductance, in the previous cases I neglect all the leakage inductance value. You know, in an ordinary equivalent circuit you have this primary winding resistance, with series of that you have a leakage inductance path for the primary side, and the secondary side also you have some leakage inductance path. So I neglect those things. However, I cannot set it to 0, so I would add 0 points. This is asking in, yeah, I will say 0.0000000000001, right? Why I am interested to set all these values in SI units? Because this is asking from SI units. Primary winding inductance is in Henry, right? So when I set these parameters as this 0.001, 0.110, I should get my identical transformer. This does not asking the secondary winding inductance because it can automatically calculate by this simulator by place. So this is my third circuit. I can copy this and I can replace my inductor. I don't need any couplings here. And also you have to remember that when I built this transformer, I already gave the primary winding inductance parameter and the secondary winding inductance parameter to my model. So I should remove these two values because those are inbuilt in this block, and also this one. Now this is my output voltage. Right. Now let's compare these three. This one and my second transformer output and the third output. Let's simulate and check the results, whether I have the same output or not. I think I can get the same output, but let's see. Yeah, all of three are perfectly identical. That means these three are identical circuits. These three are three separate approaches that I can use in PSPICE in order to build a model for a transformer, right? There may be many ways to explain a transformer, right? Now let's see the refer to primary circuit or refer to secondary circuit. How to think about that? Refer to primary circuit, from these three I would like to select this one, because this one I can separate these two, right, and redraw the circuit. Refer to primary circuit. These two I cannot do it because I cannot remove one part of this, right? So I keep these two inside, and now I would like to draw the equivalent circuit for this one. Refer to primary equivalent circuit. How to do it? As you know, when I refer my secondary to primary, I had to do some impedance transformation, right? This is my primary winding resistance and primary winding leakage inductance. This is primary winding, and secondary winding leakage inductance, resistance. Here also I have magnetizing inductance and core loss resistance. Right. Wait, I will forward the transfer module. Right. Sorry. Let's draw this nicely. Here I have two parts. This is my core loss resistance. This is my magnetizing reactance, my secondary. Secondary leakage inductance and secondary resistance, winding resistance. So this is my secondary voltage, this is my primary voltage, this part is my ideal transformer. Right. So I am going to neglect this primary winding leakage inductance and primary winding secondary winding leakage inductance. That means the mutual coupling in between these two windings are perfectly coupled. Leakage is zero. It is a good approximation, no problem. Then these two are ideal inductance. This is my magnetizing inductance. You might confuse with these two. What is this magnetizing inductance and what is this one? What is the difference in between these two? This is an ideal one. Inductance of this ideal one is very large value. This is the finite value. Right, let's see in the PSPICE. Here, this is our magnetizing inductance. Right, this is my magnetizing inductance with 1 millihenry. Here I didn't draw any ideal transformers. For an ideal transformer, the inductance value is infinity. Right. So how to draw the refer to primary circuit? As you know, when I need to transform my impedance, this is, assume this is 1 to n transformer, step up, this is R1. Now set it as an impedance, this is Z. When I need to transform this Z to this side, I have to divide this Z by n square. Right, you can just Google it and see how to do it. Right, so when we want to draw the refer to primary circuit, I just copy this and I am going to delete this secondary winding and I am trying to draw the refer to primary circuit. Refer to primary circuit, that means I don't have any secondary windings. I have only my primary winding. Right, and also I don't need any couplings because I am referring secondary to primary. So I need two resistance values because there are two resistors here. These two are added nothing this way. Refer to primary means I have to add those refer to primary elements in parallel with my primary coil magnetizing inductance. Right, so the value of this one is 10 ohms. 10 ohms, the ratio is 10. So when I want to refer this 10 to my primary side, I have to divide that 10 by the square value of the turns ratio. 10 divided by 10 square, that means 10 divided by 100. 10 divided by 100 means 0.1. Yes, this is 0.1 ohms. Then what about my load? This is my load resistance. I have to refer this from here. 1k 1000 ohms divided by 100, that is 10 ohms. My load is 10 ohms in my referred to primary circuit. Right. So this is my referred to primary equivalent circuit for my transformer. So how to check it? This is primary circuit, right? So let's check the voltage of this point and this point. Check whether those two are identical or not. Right. Yes, those two are perfectly matching. That means this is my referred to primary circuit. Let's see the output voltage. This is the output voltage of my original circuit, and this is the output voltage of my referred to primary circuit. Let's see the output voltage. Do I get the same output or not? I don't get the same output. Why? Primary voltage, I get the same output because this is the primary referred to primary circuit. But when I consider the output voltage, I didn't get identical values. Right? Is there anything wrong with this? No, I don't think so. How do you check it? Right. So let's check the power. Let's check the power consumption across this load and this one. Now check whether those two are identical or not. Yes, those two values are perfectly matching. That means the power consumption is same. That means the second circuit we already drawn is the perfectly matching to the referred to primary circuit of the previous one. So here when you see this plot, it is not nicely drawn because of the resolution. Now I would like to increase it. Options, add one more zero. Right, what is the most interesting thing is the power transfer. In all these four circuits, when you measure the power across your load, all four are identical. That means all four are equivalent circuits to our transformer. 1 to 10 step up transformer. Right, now you can see a better curve. Right, now would you like to consider the energy? How much energy dissipated across my load within some time? Now this is power. I already done a video about that, but however I would like to tell it again. If I need how much energy dissipated across my load, I can trace S. S means integration. S, the power value of my load resistor. Load resistor is R21. R21, yes. This means I am integrating my power curve with respect to the parameter in x-axis. X-axis parameter is time. That means I am integrating my wattage power value with respect to time, which is giving energy. Right? So now can you see? My power values are very high values, but energy value is very low value. How to see this? I remove this both values and I can see the energy values properly. Now let's see. Here I have nearly 4 kilowatts of power, and consider these time values 10 milliseconds to 20 milliseconds. Small time. Energy means power times time. Because of this time is 10 milliseconds, right? Here you can see the energy is increasing gradually. Right? Energy is increasing gradually. When the time is 100 milliseconds, the energy dissipated across the resistor is 200 joules. When you consider an inductor as your load, how it happens? Is it dissipating the energy? No. An inductor is not dissipating the energy. It is only transferred the energy. It is absorbing the energy and releasing energy as a capacitor. You can check it by adding some other element, adding an inductor or a capacitor as our load. Right, so now I'm going to wind up because now this is too much. Now you have 4 identical circuits. One of these is you are referred to primary circuit. So this is a way to implement a transformer in 4 approaches. Right, so that is for today. Thanks for watching. Bye.